Hey, what's up, chemistry people? It's Mr. Boylan, and today, what the heck are we going to be doing? It's a doozy. We're going to be able to identify and classify precipitation, acid base, and redox reactions, and then translate an observed chemical change into a balanced chemical equation and justify the choice of equation type, either molecular, ionic, or net ionic, in terms of utility for the given circumstances. Whew. All right, let's break that down and just take a look at the two parts here, essentially. First, we're going to identify and classify reactions as either precipitation, acid, base, and redox reactions. And then secondly, you're going to translate an observed chemical change, so like stuff you observe in the lab, into a balanced chemical equation. And depending on what it is that we're doing with that observation that you make in the lab, you may need to put it in a molecular equation, an ionic, or a net ionic equation, just depending on what it is that we're going to be doing. So that's what we're doing today. Sit down, get ready, here we go. So first things first, we're going to talk about those different types of reactions, the first of which is a precipitation reaction. And again, different circumstances are going to call for equations to be written in different forms. One such situation is where we've got this double replacement reaction in which a precipitate forms, in which we call a precipitation reaction. Generally, in a precipitation reaction, your reactants are water-soluble ionic compounds that dissociate into anions and cations. Yet when you combine these two aqueous solutions together, one of the aqueous anions and one of the aqueous cations come together to produce that insoluble precipitate. Okay, and we're going to use a quick here animation to help you better visualize what's going on in a precipitation reaction. As you take a look, we will use the sodium chloride solution here and the silver nitrate solution. As we mentioned earlier, they are both aqueous solutions. The ions are dissolved in solution there. They've dissociated, they're dissolved in solution. But notice what happens here when we mix the two solutions together. One of the anions and one of the cations comes together to form a precipitate. And so as you look here at the animation, it's the silver cations and the chloride anions that come together and precipitate out of solution. The sodium ions and the nitrate ions sort of stay dissolved in solution there. Now at the macroscopic level, you'll sort of see just what happens here on the left-hand side, this white solid precipitate beginning to form at the bottom of your beaker. As we take a look at sort of what this may look like in equation format, precipitation reactions are examples of double replacement reactions. One example of a double replacement reaction is silver nitrate, aqueous silver nitrate being mixed with aqueous potassium iodide. Yet when mixed together, the silver cations and iodide anions come together to form a solid precipitate. The potassium nitrate remains dissolved in solution. Again, double replacement reaction. The silver iodide is our precipitate. Boom. The next type of equation we need to talk about is an ionic equation. A complete ionic equation is one in which you start with the full equation or the molecular equation, and you split any aqueous substances into their ions, but leave any non-aqueous substances intact. So anything that's a solid, anything that's a liquid, anything that's not aqueous is gonna stay together. Your spectator ions in an ionic equation are those ions that are found in exactly the same form on both sides of the equation. In other words, they do not change or take part in the reaction, so they're just spectators. They just watch what's happening. They must be removed when writing what's called the net ionic equation. And the net ionic equation then is simply that balanced chemical equation without the spectators. It's just focused on the species in the reaction that actually undergo some sort of chemical change. All right, so let's take a quick look at how we can work through converting between a molecular equation to a complete ionic equation to an overall net ionic equation. As you look at this equation, we're going to break apart anything that is in solution into its individual ions. So zinc nitrate, because it is aqueous, would become the aqueous zinc ion, and 2 because there are two of them in solution, nitrate ions. We would also split up the ammonium sulfide, as it's also an aqueous solution here. We're going to get 2 ammonium ions, again, because of that little subscript of 2 ammonium ions, and 1 sulfide ion in solution. I'm going to shrink this down here a little bit. On the product side, we're not going to split apart the zinc sulfide because it's a solid precipitate, but we will split apart the 2 ammonium ions and the 2 nitrate ions. So here is our complete ionic equation. We've simply taken the molecular equation and split apart anything that's an aqueous solution and kept together anything that's a solid, liquid, gas, anything that's not aqueous. All right, to go from a complete ionic equation to a net ionic equation, I just want you to think of any spectator sport like football or soccer, and think about in the equation, are those things simply watching the action happen, or are they actually involved in the chemistry? So as you look to determine which of the ions are spectator ions and which of them are actually involved in the chemistry in this reaction, we'll start first with the zinc ion. On the reactant side, it appears as an aqueous ion in solution, but in the product side, it has formed a precipitate with the sulfide ion. So the zinc ion is a player, okay? It is in the game. Nitrate, on the other hand, is dissolved in solution on the reactant side, and it's dissolved in solution on the product side. So the nitrate ion is also, is going to be a spectator as opposed to a player. Ammonium, similarly, on the reactant side is a aqueous ion. On the product side, it's also an aqueous ion. And so the ammonium is going to be watching the chemistry happen. Sulfide is an aqueous ion in the reactant side, and on the product side, it has formed this solid precipitate. And so our sulfide ion will also take part in this reaction. So our net ionic equation is simply going to be the zinc ion plus the sulfide ion forming the zinc sulfide. These guys right here are actually playing the game. They're doing the chemistry. They're not watching it happen like our spectators are up here. They're actually making the chemistry happen. And that brings us to our third classification of reaction, which is an acid-base reaction. We're going to start with a couple of quick definitions here. An Arrhenius acid is a substance that contains hydrogen and releases those hydrogen ions in solution. An Arrhenius base, on the other hand, is a substance that releases hydroxide ions in solution. And then when you mix an acid with a base, essentially you get an acid-base neutralization reaction. Again, that Arrhenius acid and Arrhenius base react to produce salt and water. As we look at a quick example here of an acid-base neutralization reaction, it is an example of a double replacement reaction. The example we're going to use here is hydrochloric acid plus sodium hydroxide to form water and sodium chloride. Again, we've got a switching of the ions here in a classic double replacement reaction. We're just looking at an acid and a base as our two reactants. Water and some aqueous salt will be formed as our products. As you look, though, it's important to recognize that in an acid-base neutralization reaction, the net ionic equation is the reaction with the hydrogen ion from the acid with the hydroxide ion from the base to form that liquid water. Which brings us to Leo and what Leo says. Grr. Our final type of reaction that we're going to classify here are redox reactions. A redox reaction involves a better understanding of something called oxidation states. And oxidation states or oxidation numbers are simply charges that an atom actually has. We're talking about ionic compounds, or in a molecular or covalent compound, it's a charge the atom would have if the compound were ionic. So essentially, it's just a little bookkeeping method that we use in chemistry to help us better understand what's going on with the movement of electrons in chemical reactions. Some rules in terms of how we assign oxidation numbers. So why are these important? Oxidation numbers are used to help us determine what's being oxidized, what's being reduced, what's losing electrons, what's gaining electrons, and what's called a redox reaction. Some quick rules here for assigning redox or oxidation numbers to atoms. Any element, when uncombined as the free element, is going to have an oxidation number or oxidation state of 0. So chlorine, iron, sulfur, again, your diatomic or multiatomic states, doesn't matter, it's going to have an oxidation state of 0. If you're assigning numbers to atoms in a compound, the sum of the oxidation numbers in a neutral substance or a neutral compound is going to be 0. In an ion, however, the sum of the oxidation numbers has to equal the charge. A third rule then, as you assign oxidation numbers, group 1 atoms in compounds will always have oxidation numbers of +1, group 2 always +2, fluorine will always be -1, oxygen almost always -2, and hydrogen almost always +1. As you think about those binary compounds with metals, so in an ionic compound, the group 17 elements are -1, group 16 are -2, and group 15 are -3. Essentially following the rules for ionic compound nomenclature. Once you have assigned those oxidation numbers to each of the atoms in your reaction, you can then begin to work through redox reactions. And again, basically, a redox reaction is simply a reaction in which we have a transfer of electrons. If something accepts electrons, or if it gains electrons, we say that it's been reduced. If a substance loses electrons, we say that it's been oxidized. Again, during redox reactions, electrons are transferred from the species that is oxidized to the species reduced. And we can identify a redox reaction simply by writing the oxidation number above each element in the equation. And anytime we have a change in oxidation number, it's going to indicate for us that we've had a transfer of electrons, and thus we've had a redox reaction occur.